Hello everyone, welcome to the IGCB 2021 competition workshop about the NIR-ISL 2021, namely NIR-IRIS Challenge Evaluation in Non-Cooperative Environments, Segmentation and Localization. First, let's start with the introduction and a word about this competition. This competition was jointly held by Cai Yongwang and Qichuan Tian from Beijing University of Civil Engineering and Architecture, Zhao Fenghe from Beijing University of Post and Telecommunications, and Yunong Wang, Kunbo Zhang, Javad Mohammed, Tian Haolu, and Zhe Nansun from CASIA. And this is me. I'm currently a lecturer, and welcome to visit my homepage. The PPT shows the schedule of this competition. The competition was held from February to May, about 3 months. Now we officially announced the top three winners of this competition. The first place is Yi Wenzhang, Tian Baoliu, and Wei Yang from the School of Biomedical Engineering, Southern Medical University, China. The second place is Dongliang Wu, Yinfeng Liu, Ruiye Zhou, and Hui Haiwu from Shanghai University of Electric Power, China. The third place is Hao Zhang, Junbao Wang, Jia Yi Wang, and Wan Tongxiong from College of Sciences, Northeastern University, China. Congratulations to them. We also thanks for the sponsorship by attending Academy for Intelligent Recognition Technologies. Second, I will introduce some details about this competition. Why we held this competition? Let's start with the background of iris recognition. As we all know, iris recognition is being developed from the constrained settings to the less constrained settings, generating a more long-range, visible, and mobile iris recognition technologies. Especially in the COVID-19 period, less constrained or non-cooperative iris recognition becomes more and more important, which can effectively supplement or replace masked face recognition. For less constrained scenarios, iris images inevitably suffer from all kinds of noise, such as blur, specular reflections, shadows, occlusions, and off-angle. Clearly, compared with the normal iris images, these degraded iris images bring great challenges to iris segmentation. Hence, our competition focused on the iris segmentation in non-cooperative environments. As illustrated in the figure, we know iris segmentation is in the pre-processing stage, and the red line labeled part all belong to the iris segmentation. Iris segmentation connects the iris normalization and feature analysis, and is the basis of all downstream tasks in iris recognition. So, what is the iris segmentation? Let's do a review. We looked up the early literature and found this definition in the TSMC cybernetics given by John Dogman. He says iris segmentation is to locate the valued part of the iris for iris biometrics, including finding the pupillary and limbic boundaries of the iris, also termed as the inner and outer boundaries of the iris, localizing its upper and lower eyelids if they occlude, and detecting and excluding any superimposed occurrence of eyelashes, shadows, or reflections. I think the following figure gives a very clear explanation. The definition also provides the solution of iris segmentation about the three parts. But if we carefully analyze the definition from the view of the whole iris recognition, we can find the task of iris segmentation can be concluded as two subtasks. One is to update the perimeters of inner and outer boundaries of the areas, which are used for areas normalization. This is the first step of the definition. We call this as areas localization or perimeterization. Two is update the noise-free areas texture region, generating a binary areas mask, while the valued areas region is labeled in white. This is the result of the last two steps of the definition. The areas mask is used for ignoring the evaluated pixels in the feature analysis. We also narrowly refer to this as iris segmentation, just following the definition of semantic segmentation. About these two subtasks, many traditional methods did well in the normal iris images, but was not robust in those relatively noisy iris images. Recently, many DL-based methods have claimed they can do better in the iris segmentation, but in fact, they were good as they claimed. We select several methods published in recent years. As shown in the figure, we can find that these methods were mostly based on FCN, namely fully convolutional network from semantic segmentation, but they only predict the average mask, not including the average boundaries. Hence, they are incomplete. To remedy this, recent methods considered some post-processing operations to parameterize the iris mask. For example, this method proposed to use a circle Hopf transform to locate the iris circles on the iris masks. And the newest method proposed two methods included the mass center framework and the circle fitting framework. Although they seemed to be effective, is it enough? In fact, we found that only post processing on the iris mask is not enough. For the following figure, a circle of transform failed to locate the suitable iris boundaries. Since the iris mask is not irregular, it's extremely noisy and incomplete. Model the iris boundary in the DL models. We recently proposed a new method, namely iris fastnet. It used the unit framework to actively predict the iris mask and iris boundaries and achieved very promising results. The perimeterized boundary does not depend on the iris mask, just use the predicted iris boundary maps. Hence, good results are acquired as the following figures show. This is the first initial attempt to use the DL method to actively show the iris localization. So we want to continue this direction to find better DL models to achieve more accurate iris segmentation and localization models. Hence, we held this competition. Of course, there were two well-known challenges for iris segmentation, namely NICE-1, held in 2007. It aimed at segmenting the iris mask of visible iris images from UV iris version 2, and MICO-1, held in 2015. It aimed at iris segmentation for mobile iris images. Although the two challenges had greatly promoted the development of non-cooperative iris segmentation, they also have some limitations. First, the two iris segmentation benchmarking competitions are mainly focused on the visible iris images from Caucasian people. Two most submitted methods were developed based on traditional image processing and pattern recognition methods, rather than deep learning technologies emerged in recent years. Three, the benchmark design is relatively small. The iris boundary is not directly evaluated. Based on this above analysis, we decided to hold a new iris segmentation benchmarking competition at IDCB 2021. Next, I will introduce the process of the competition. The competition used three datasets, including Cassia Iris Asia, Cassia Iris M1, and Cassia Iris Africa. These are NIR-ISL images of having different noisy types and capturing settings. Hence, they are very useful to assess the performance of iris segmentation in non-cooperative environments. Our training iris images from three datasets were made available to the participants together with the ground truth segmentation masks and localization boundaries at the start of the challenge. Besides, our testing iris images without ground truth were also released to the participants along with the training datasets. The Cassia Iris Asia dataset is a union of long-range Cassia Iris distance as the newly collected Cassia Iris complex. The Cassia Iris complex is also renamed as the Cassia Iris degradation. More details about this dataset can be found at the following paper. Cassia Iris complex including two subsets, namely occlusion and of angle. The Cassia Iris M1 is a mobile iris dataset. The Cassia Iris Africa is the first large-scale black Africa iris dataset to the best of our knowledge. It contains various noise factors such as occlusions of angle, illumination variations, dark colored iris, and skin. It should be noticed that for the annotation of inner and outer iris boundaries, we manually draw the inner and outer ellipse curves to approach the real iris boundaries as much as possible, just shown as above images. The competition requires to train three models on above three datasets that perform a within dataset evaluation. Especially, Cassia Iris Asia were split into three parts corresponding to Cassia Iris distance, Cassia Iris complex occlusion, Cassia Iris complex of angle, and their performance were reported respectively. For the evaluation of iris mask, we followed the nice one and used the E1 and E2 as the metrics. These two metrics evaluate the average error rate. The smaller the value, the better the iris segmentation. For the evaluation of iris boundary, we used the DIS index as the hot-off distance as matrix. The DIS index is employed to measure the overlapping ratio between the predicted iris boundary mask and its ground truth boundary mask. Here, the iris boundary mask is referred to as internally filled iris boundary, as shown in the left. The hot-off distance is employed to measure the shape similarity between the predicted iris boundary and its ground truth boundary, as shown in the left. The DIS index measures the average accuracy rate. The greater is the better, while the hot-off distance measures the average error rate. The smaller is the better. Overall, we have four evaluation metrics of having different matters as they cannot be summed. Also, we have five testing datasets as we have 20 score per method. How to rank their overall performance? Here we adopted a standard competition ranking, namely 1 to 4 ranking. For example, giving the DIS index score of four methods are 0.8, 0.7, 0.7, and 0.6. According to the matter of this index, the greater is the better, as they are ranked as first, second, and first. Here, the 2 means the items that compare equal receive the same ranking number. The sum of these 20 ranking scores were then used for the final ranking. To be specific, a smaller sum stands for a better overall performance. Therefore, the model with the smallest sum came first in the final ranking. At last, we gave the summary of the submissions in the competition. We received 30 team registration for NIR-ISL 2021, who were from different academic institute or industry organizations in different countries. Only 14 teams took part in the final round and submitted a total of 27 valued models for both areas segmentation and areas localization. The top three results are acquired by the Laoyang's sprint team, whose ranking sum is 15.6. Next is SUEP Pixel SUR, whose ranking sum is 120. And then IQ, whose ranking sum is 134. The details of their method will be explained by them later, and other methods descriptions can be found in our summary paper. Here, we also show some visualized results, where A and E shows the original Aries images and the corresponding ground truth of Aries mask and inner and outer boundaries of the Aries. Then B, C, D shows the Aries segmentation and localization results from the best three models. And F, G, H shows the Aries segmentation and the localization results from the worst three models. As is shown, the best three models are superior to the worst three models in most images when looking at the quality of Aries segmentation and localization. Finally, we give some open questions about Aries segmentation. First, how to conduct the Aries location using the learning-based method if without the annotations or with limited annotations. Two is how to develop the lightweight Aries segmentation model, which is very important for practical deployment. Three, three is how to develop more accurate Aries segmentation models, such as using domain knowledge or novel learning methods such as transformer. Four, new Aries segmentation manners for DL-based Aries recognition. For example, some methods have claimed that they do not need the Aries localization or Aries normalization. Five, more application scenarios and richer designs are also required. Here are some useful links, and welcome to visit it. Here we also provided the competition insight. You can visit the GitHub. Finally, we will thanks for all participants. Thank you. Any question?